Why does torque causes things to rotate, and that too about the center of mass? Most of the physics and engineering students are well familiar with the concept of torque, while still finding it difficult to explain the simple phenomenon that we are going to discuss today. To answer this question, let's first understand torque. Torque is the measure of how much a force acting on an object causes it to rotate. If a force is acting on an object, then only the component of force perpendicular to the radius vector, where radius is measured from the center of rotation, will produce a torque. Let us suppose a hypothetical rod made up of 7 particles. Hypothetical because generally we cannot work with a rod made up of 7 particles. Applying a force perpendicular to the rod's length dimension on the 7th particle should cause it to move in the direction of the force. Pretty simple and straightforward, right? No. It is clear from the figure that BC dash is greater than BC, but that is not possible because first of all, as the bond length increases, it tries to pull the 7th particle back to the same place, and now there are 2 forces acting on the 7th particle whose resultant does not point in the same direction as the applied force. And even if we suppose that the translatory motion continues, a time comes when the 7th particle is no more a part of the rod, which is not allowed, ripping off particles from the rod. Therefore, the particle will not follow a translatory path. See, I told you. Let us try something different. How about making 6th particle the axis of rotation and rotating it, since the resultant in the previous case causes it to do so? Doing this will not even weaken the bonds. Well, even this is not possible, because we are disturbing the linearity of the rod, and it would look something like this after bending. And since this is also prohibited, hence the particle will neither move the previous way, translatory motion, and nor move this way, rotation about the 6th particle. Let us refer to the basic concepts of physics as given by Sir Newton. Applying a force on the 7th particle will for sure move the 7th particle, because an unbalanced force on any mass will always cause an acceleration in it. But since it is connected to the 6th particle, and since the rod cannot bend or break away, hence the 6th particle can also rotate to allow the 7th particle to move, and at the same time will prevent any damage to the rod. Are we done? Not yet. Don't forget that we are still left with the 5th particle, the 4th particle, the 3rd particle, and so the entire rod. No problem, we can apply the same concept to all the particles. Therefore, all the particles can rotate about their own axis along with revolution, such that the rate of revolution is same as that of rotation to prevent the neighboring particle from breaking away. Hence, all the particles rotate like this, rotating the entire rod like this. But now the problem is that if the rod is rotating, there needs to be an axis of rotation. Well, if there is one, where is that? Probably here, or here, or more symmetrically here. You all must be familiar with the Newton's third law of motion. For every action, there is an equal and opposite reaction. Or, forces always act in pair, and there is no such thing as independent forces, at least not in this universe. So even in the case of a rotating rod, this statement can be used to eliminate some of the axis of rotation. Rotating bodies are acted upon by centripetal force, while they apply an equal but opposite force on the other body known as centrifugal force. If any of the one is absent or greater than the other, then the rod won't rotate, or the situation, the rotation, is hypothetical. In our rotating rod, there is no source of centripetal force because no external force is holding the center of rotation. It is only the location of center of rotation that is going to affect both the forces. As our first attempt, we will try to find any imbalance in forces in the first situation. Here, the center of rotation is particle 1, and since all the masses are on the one side in this situation, there is no force, centripetal, counteracting the centrifugal force, inertia of the particles resisting any change in velocity. Hence, this situation is not possible, as there is no action present for the reaction. Rotating the rod about the 2nd particle might work. In this case, from the perspective of collection of particles on any one side of the center of rotation, say the side consisting of 3rd, 4th, 5th, 6th and 7th particle, the centripetal force is provided by the collection of particles on the other side, that is the side consisting of the 1st particle. It is clear that because of more number of particles on one side of the center of rotation, and because of their larger distances from the center of rotation, more massive side is going to possess larger centrifugal forces as compared to the centripetal force provided by the less massive side, and from the perspective of the less massive side, the centripetal force will be way more than needed. Therefore, due to the imbalance of forces on both sides of center of rotation, the center of rotation is not particle 2. Similarly, center of rotation cannot be either of the following. But still, there is one particle left to be designated as the center of rotation, that is, the particle exactly in the middle, the fourth particle. And this, as we'll come to know, works just perfect. Here, the magnitude of centrifugal forces experienced by both the sides is exactly equal, as we know that from the perspective of collection of particles on one side, the collection of particles on other side provide the centripetal force. Hence, in this situation, both the centripetal and centrifugal forces from any perspective are equal. Therefore, particle 4 is the center of rotation of the entire rod. Now, so as to generalize the situation, we can say that when a torque is applied on any object, the object will always rotate about the same fixed point, and the fixed point is such that all the planes containing the point divides the object into two parts such that both the parts produce equal centrifugal forces when rotated. This point is known as the center of mass. The equal centrifugal forces act as centripetal for each other, supporting Newton's third law. So, our rod will rotate like this. Special thanks to Sir Isaac Newton, the person who laid the foundation of classical physics and without whom this explanation wouldn't have been possible.